Okay, we are back with the final practicum for Project 2. We're going to do visibility analyses here in grass. So we have a new map set that I created in our HASA WS UTM Zone 36 map set called Visibility. Now I've pre-done some of these because I was making examples for a lecture and for another project that I'm working on. So you will want to create that map set. Again, you can use whatever tools you want, but the easiest way is to right click on the location, create map set, and call it visibility or visibility analysis or something of that particular nature. So I've already preloaded a couple background maps. I've got the Nabatean towers and red dots over here, and I've got a shaded relief with the DEM on it in the background. And what we are going to do is to undertake scaffolding through the different types of visibility analyses that we talked about in Monday's lecture. And we are going to find all of those things pretty much in the terrain analysis and then in some add-ons. What we can do, there are a variety of ways of achieving this, but the simplest one is going to be to start with the Viewshed analysis. And so we're going to use the Viewshed module. And over here, again, like all modules, there's a manual that you're going to want to look at to read about the specifics of it and what all the flags do and how the algorithms work. And again, like many of the manuals in GRASS, it's very, very helpful, very, very informative, and of course gives you references. But to get jump started on here, you really just need to input that elevation map. So we're going to go ahead and put in our HASA 30-meter clipped watershed because we're just working again in our watershed boundaries. We'll set an output name in a minute, but first thing we need to do is to decide what the viewpoint is going to be, and we need to do this by extracting some coordinates from a meaningful place. And I am going to pick a site. I'm going to pick one of these towers sort of off to the side over here, just for fun, to give us a sort of counterpoint to the one that I showed in class. So again, making sure our query tool is selected and our tower vector points map is selected over here. I'm just going to select that site, and in the output I have the coordinates which we want, and this particular time I'm kind of curious what number it is because I want to label this according to the site number 858, one of the Nabatean tower sites. So back in our Viewshed we can paste in those coordinates, and now I can call this I'll just call it Tower 858 Viewshed. Okay. Before we hit run, there are a couple of settings that we want to check. The Settings tab lets us change the observer elevation. So remember, there are two offsets. By default, the DEM has the elevation of the ground surface, but humans could be standing, they could be laying down, they could be on horseback, or in this case, they could be up in a tower. So I'm going to elevate this person 5 meters above the ground, assuming that the tower is going to be at least 1 story, maybe 2 stories. I mean, we don't call them towers if they're not more than 1 story. So we're going to assume 5 meters is about right. If we had some real information about the height of this building, we could do that and then add the height of a person, on top of it to get the exact height off that ground surface pixel. And then we can set offsets for target elevations. Remember, are we looking at the ground? Are we looking at humans walking, humans on horseback? Are we looking at trees? Are we looking at people standing in other towers? So for the purposes of the watchtowers, we're going to assume they want to find people. So let's just assume they want to watch for people walking, and about 1.75 meters is an average human height. Okay, we could set a radius in meters where we don't care about the viewshed beyond that, so only a kilometer away. We could just do this. The only benefit really is that it might speed up the calculations a little bit. And we could also set the azimuth, the compass direction that the tower, that we only care about the view. And again, the only reason we'd want to do this really is to speed up the calculations if you're running into problems, because in general, most of the time we care about the full view shed, and we'll deal with it later. We can consider the effect of atmospheric refraction, and since these are human models, we do care about what people could really actually see. So again, as distance increases, there's dust and the air itself, and also shimmering effects from heat and stuff. And so really there's a functional distance where even if technically the curvature of the Earth doesn't fall off before then, functionally you're really not going to be able to make out any details. And so you can check that box, and if you know anything about this and you read the manual, you could change this if you're in a really dusty place or really glary, heat mirage effect kind of a place. You could change that value to account for that. We can go output format 0 invisible, 1 visible, or null invisible current elevation. I tend to just go 0 and 1. It's pretty useful. There are reasons to do the other one, but you can decide how you want to do that. And then finally, we want to consider the curvature of the Earth. Otherwise, we're flat earthers, right? So let's do that. Again, the only reason not to is to speed up the calculations. And again, there are a couple other things. If you're doing a really big area, this routine can be memory intensive. So I'm going to up it to 50,000 megabytes of RAM. You should do whatever your computer will let. Usually, you're probably working with at least 4, hopefully a little bit more, like 8 gigabytes of RAM, so you could maybe set this to like 7,000 or something like that. And if you need to, you can set a specific directory to hold temporary files. But this should be good in general for me. I'm going to hit run, and I'm going to let it do its thing. And that was actually relatively quick. And over here, we have our map where the purple is not visible and the yellow is where it is visible. And if we want to quickly turn the 0 invisible, the simplest way without doing anything permanent is just to go into the properties for that raster, and under selection, all we do is say all I care about is the value of 1, and it will just turn all other values invisible, and since the only other value is 0, it goes away. And now we can see the view shed is the yellow areas for that particular site over here. And if I just drag it below, we can actually get the tower on top. And so you can see this particular tower doesn't have a very big view shed. It's really just looking kind of this way. Remember, this part of the landscape we determined in class, and which I'll show you again when we get to the CVA, is just highly visible. So they're not really keeping tabs on this necessarily, but these are the areas where this particular site could be looking at. And if we look at the one that I showed in class, which is a different site, I'm just going to do the same deal with the properties on that one. Set the selection just to view 1. We can see sort of difference between those two. And, they're both in yellow, so one thing that I can do is quickly change the colors using the interactive color management tool, which will pop up here. And yeah, it's going to have a bunch of weird stuff, but we really just need to change this value. I'm just going to change it to red and just see how it looks. Okay, so now we have the two tower sites sort of side by side. We see the overlap is this highly visible area, and the rest of it is kind of independent from each other, other than the ridge to the north over here. These two different sites have, I think this particular site over here is 858, or sorry, 158, which is the one I showed you in class, and 858 over here. They have really different view sheds, which is kind of an interesting thing. So again, one of our working hypotheses is that these towers were situated to have unique view sheds. They're each looking at a very particular part of the landscape. And we've just done two. We want to do all of them, or at least a good sample of them, to get confidence that that hypothesis is remaining true. Okay, so that is an individual viewshed. And again, we would go one by one. We could do this clicking on the coordinates, putting them in, generating individual viewsheds. What we really want to do is to automate that procedure. And I have created an add-on tool that basically does that. And it also will automatically calculate the cumulative viewshed, or the visual scape, as we talked about in class. So again, settings, add-on extensions, install, and then under the raster menu, you'll go down to the very bottom, which is our Viewshed CVA. Now this other one, this exposure, I didn't write, somebody else did, and it calculates an exposure index. So it's another really interesting visual viewscape kind of tool. So let's install our Viewshed CVA, and once it's done, I will show you some of the convenience tools that I've built into that. Sorry, let's type it in here. Our Viewshed CVA. Okay. There we go. So this module, it does have a little, help that I wrote, although it's not as good as the original Viewshed module. This is built on top of our Viewshed. So everything that applies in our Viewshed applies here. This is just a convenience layer to automate a lot of the generation of the Viewsheds that you need to do a CVA. Because remember, you got to make all the Viewsheds, or a lot of the Viewsheds, and then stack them up, adding them to get the cumulative value. So again, you need the input DEM. This could be the same one that we used before. And then you need an input vector map. So you need site points, viewpoint points. So if you're going to do like the top of peaks or something, you need to generate that as a points map first, because this is going to loop through all the points, generating a viewshed for each one, and then stack them together. So here you can very quickly just put in the Nabatean towers, and then you can create the output cumulative. Now, I've already done this because this will take a significant amount of time. This is a set it, go away, get some coffee, come back kind of a deal. And here we have what I call it, Nabatean Towers CVA. So this is the cumulative viewshed of all the towers. That's the kind of visual scape we're creating. And then optionally, you can type in a lot of the same things we did before, considering the curvature of the Earth, considering the effect of atmospheric refraction, and you can keep all the interim viewshed maps. You may want to do this if you want to generate a whole bunch of viewshed maps. That's one convenience thing that this routine can do for you. Whether you want the CVA or not, if you want a whole bunch of viewshed maps and you don't want to be querying and typing in coordinates for all of those vector points, this can do that for you, and just, again, set it and forget it and walk away. And it will automatically name the viewshed with the ID number from a column in the database, which could be, for our particular one, site num. So we can type that in there if you wanted to keep all the viewshed maps. Now you may decide you want to, you might not. Again, they can take up a significant amount of disk space, so if you're running low on disk space, I would say you don't want to do this. All of these maps will be made, so you do need some disk space available for this routine to run. But if you don't want to keep all those interim viewsheds, don't check this box, and the routine will automatically clean them up and throw them away at the end. And again, then you can format them either way that you want over here, and you can change the observer height, right? So in this case, let's do 5 for the observation point, and let's leave 1.75 because, again, human height. And I would give it all the RAM that you can get at this particular moment. And you would hit run, you would walk away for coffee, but I've already done it just to save ourselves some time, and we have the map like we showed in class. So what I'll do is very quickly just drape it on the hillshade because I think it will help us to see the topography underneath. There we go. So let's go ahead and zoom in over here. And this is showing us the areas of the landscape that are commonly viewable from more than one tower. Now the total number of towers is something like 50 or close to 50. And when we put the scale, the raster legend for the Nabatean Towers CVA, let me go ahead and put the background on. And it's going to be a little bit weird to look at first, but let me just resize it, put it over here. Just make it a little bit bigger for us. Maybe a little bit bigger than that, eh? I guess I have to make it taller is what I need to do. Let's stick it like so. Now we can see how the values are spread. So actually, the functional largest number in the map is 40. Okay, so you know, if we wanted to get the total count of the actual towers, let's do that with vinfo, and it'll tell us how many are in there. 52 towers. Okay, so even though there are 52 towers, there is no single point on the landscape that is visible from all 52 towers at once. Instead, the most visible part of the landscape is visible from only 40 of the 52. And so each color that we're looking at over here, each color gradation, is scaled to the number of tower sites that are being able to look at that particular pixel. And the values that have those big numbers are all on this northern ridge. And again, it could be that they're all situated to look at that ridge, but what we'll do next will verify or deny if that hypothesis is true. The other places that are highly visible seem to be over here to the southwest kind of areas, and also internally along some of these ridge lines. And there are actually quite a bit of the landscape that's really only visible from a small number of sites. We could change the colors if we wanted to see if putting some sort of a logarithmic scales reveals a little bit of patterns. So let's go ahead and do that. We're gonna stick with that Viridis, but we're gonna do logarithmic and just hit run on it, and it'll stretch those colors so that you get more variation in the low values and less in the high values, and it lets us see a little bit more clearly which parts are observable by a small number of sites, these tower sites. And now we get a better sense that each site, again, seems to have a fairly unique viewshed, or one that's only shared with a small number of other tower sites. And a lot of the coverage of these towers is actually internal, but there's a lot of them right here, so maybe there's a route or a road that comes through this particular zone here, and those towers are looking out for it. And you have a couple of these outliers. Maybe they're outposts. We don't know. I'm not an expert in the Nabatean period. I do know that in the Roman period there is a road. It comes through here, and the Hajj road is off to the east, which all of these later roads are probably built on top of earlier roads. So, and I know the Nabateans were traders, and they were moving stuff around, so that kind of makes some sense. Wadi Hassa is a big thoroughfare for this part of the world. Now, I mentioned in class, the pixel values, again, are the number of sites that can be seen. If you want them to be percentage visibility, you have to take the total number of input sites, which was 52 in this case, and in the raster calculator, we just do some division. So we grab our CVA map, we divide it by 52, and we can just rename this % like so, and we can hit run on that. And we would need to actually, we need to put that as a decimal point, because grass is funny. If you give it an integer like that, it will create an integer of 1 And I should have known that, but we're going to overwrite that. Hit run. And once that's finished, now we'll see it. Now the pattern will be exactly the same, but if we put that percent map into the scale, you will see that it now is a continuous variable between, let me just resize that, between 0 and technically 1, but remember 40 was the maximum value, so it's 0% to 77% is the functional maximum visibility score, using the tower locations as input. Okay, so we want to see if that actual ridgeline there is something that the towers are uniquely looking at, or if it's just a generally visible part of the landscape. And to do that, what we need to do is to generate a bunch of random points so that we can calculate what we call the total viewshed, or the general visibility of the landscape. And so what we can do is, using the watershed as the sort of input zone, we can generate a certain number of random points within that. So we go to raster menu, we go down to generate random cells, and we pick the generate random cells, and vector points are random. And for the input raster map, we're going to pick our clipped watershed, and we could just put a specific random seed here. This is just for replicability. If we needed to do this, we would set a specific one. Or we could just do this to get a completely kind of random input seed. And what we'll do over here is put a total number of points. So for you, depending on your computer and how long the Viewshed CVA is taking you, you want to scale your expectations according to what your computer can do. On my computer here, I have done one with 1,000 points. I could do one with maybe 10,000 points, and it wouldn't take terribly long because this is a really good computer. But on your laptop, you might want to stick to something like 100 points. So you can put a specific number over here, and then you put the name of the output map. We'll call it rand points 100, and I've already done this, but I'll just overwrite it so I can just show you real quick what that looks like. And it is gonna put the random points, but let me just change the color so you can actually see what they look like. Okay, so there is 100 points spread across the map over here. And 100 points is not that many, but it's enough because they're spread out across the whole watershed. Now I'll just show you the 1,000 points to show you the difference, and you can kind of see that, you'll see that the colors are, let's do them in orange. So you can see like 1,000 points is a lot more, right? So 1,000 points is going to give you much better representation, a sample of the possible total number of possible viewpoints, which is every pixel in the landscape. If we did every pixel, even this nice computer would take forever to do it. So you choose a number. I would say to get a decent, if slightly potentially underrepresented sample, let's go with 100. You could pick 50 if you're really working with a low-powered computer, because again, you're doing this as a project, not as a published thing. But what we'll do is we'll get back into our Viewshed, there it is, our Viewshed CVA, and instead of the Nabatean towers, you're going to grab your rand points 100, and you're going to call this, well, just since the name of this kind of analysis is total viewshed, we'll just call it the total viewshed, like so. And of course, you're going to want to change maybe the observation points, just put it back to human height. And again, you could potentially keep all of the intermaps, but for this one you really don't need to do it. Crank up all the RAM and everything like that. and go ahead and hit run on that, and go off, get your coffee, and come back. Maybe let it run overnight, depending on how slow your computer actually is and how many points you told it you want. But it will create a total view shed. So it looks like that. So this is the one I ran with 1,000 points, and this is one I ran before that with 100 points. And you can see that again, the 1,000 one I constrained to the watershed. The 100 ones I did with the full SRTM. But you can basically see that the pattern is the same, but the scale bar will be different because, let me just put the 1,000 point map here, and you will see that the theoretical maximum for this one is 1,000, but 301 is the functional maximum. So along the ridge we get 301. Some pixel or pixels there can be seen by 301 other pixels from our random selection of 1,000 random pixels across the map. And it shows the parts of the landscape that are pretty visible. This one and this ridge line, again, are very visible. And we could, again, in our map calculator, we can create a percentage visibility from this, which makes a little bit more sense with total view shed. So take our total view shed 1,000, divide it by 1,000, and call this total view shed 1,000%, like so. And again, I did the same dumb thing, which is the fact that I needed to put a 0.0 here so that it does it as an integer, not as an integer, but as a floating point. And hit run. And when that goes, map will look the same, but when I set the scale to it, now we have it 0 to 30%. So again, 30% is the functional maximum visibility, even though the theoretical maximum would be 100% visibility. There is no cell in the map that is 100% visible, but the ones that are the most visible are definitely these ones over here. Now again, we could manipulate our color table so that we can spread those values in that logarithmic curve that will elucidate a little bit more the patterning at that small end of it over here. Did it not do it? Oh, it might not like it if it's a percentage value. And let's just make sure I picked the right map. Okay, let's set the original one. What did I do? Oh, yeah. Okay, sorry. Let's do the original one. And uncheck that. Okay, there we go. Now it works for that one. Again, our colors can be a little bit funny with those input values. But now we can see, again, using our color scheme over here, that some of the deeper canyons are very secluded. They're not very visible from large parts of the valley. A lot of the slopes are sort of somewhat visible. They're in this like somewhere between 8% and 15%. And then some of these southern slope areas are also quite visible. And if we go back and look at our Nabatean Towers cumulative view shed, we can kind of see where we're looking at. Is this the one? Yeah, this is the one that is spread out with the same logarithmic scale. So we can kind of see, I mean, really the towers don't have anything super unique about them in terms of their view, but they might be biased more towards looking over here. Even though, yeah, when we're looking at the total view shed, yeah, it looks to me that these areas over here might be just a little bit more visible from our towers than they are from the landscape. And we could analyze that statistically if we really wanted to. Okay, so that is view sheds, how to generate them, how to do the cumulative view shed analysis for input set of archaeological sites, and we did it for the total viewshed with the random points, but we could pick peaks, we could pick streams, we could pick water sources, a meaningful set of input points to do a CVA type analysis. The last thing I want to do is to switch back into our terrain analysis map set from earlier, and let's undertake prominence analysis. And again, I've already calculated some of these because these analyses do take time. And what we're going to do is we're going to use a moving window analysis to do the prominence. So we're going to use our neighbors, this moving window over here. The input just has to be our DEM, and before I set the output name, we want to set some details about the neighborhood and about the method that we want. So the minimum neighborhood is going to be 3 by 3, and we want to increase with odd numbers as we go up in horizontal scale. Remembering we're working with the SRTM at 30 meters per pixel, 30 by 30 meters. So each pixel is going to add 30 meters to our horizontal resolution that we're going to be analyzing. So 3 by 3 is a 90 by 90 meter moving window. That's the scale of the analysis. We go up to something like 9 by 9, and then we are working at a 270 by 270 or 2700, whatever, we're moving up. 30 meters times 9, we're moving up 270 meters if we go to a 9 by 9. So what we're going to do is we're going to step through a few scales. 3 by 3 might be a little bit small for this kind of analysis, because really what we're doing, remember, we're taking the elevation at the center and we're going to compare it to the average or a central tendency value in that window. And 3 by 3 is pretty small, so maybe we want to start with 9 by 9, and I have done 9 by 9, 13 by 13, 17 by 17, and 21 by 21. And again, you multiply 30 times 21 to find what that actual what the actual scale of that is. And just so I don't screw up live on camera, I'm going to use a calculator. 630 by 630 meters. And you could, again, go more than that, but that's almost a kilometer, so that is actually a pretty big scale. You could probably, to speed up your own analysis, you could probably do 9 by 9, 13 by 13, and maybe 15 by 15 or 17 by 17, and cover pretty much most of the scales, because we're going to do a scale that's relevant, and then we're going to do the global prominence, which is the average across multiple scales. So what you're going to do is choose, let's go with average. You could, there's an argument to be made that median might be a more robust statistical measure of central tendency. Mode probably isn't, that's the most common value, but let's just stick with average because I think most people kind of understand what the average is. And what you can do at this particular moment, we don't want to weight it or do any of the other things, but we can crank our RAM up. That will definitely help. If you have a computer that's relatively new, it'll have multiple processors, usually somewhere around 4 to 8 for most computers, even laptops. So I would try and give this as many as you have. My computer actually has 82 of them in here, so again, I would probably give mine more like 60,000. And I just set the name relative to that, average LEV 9 by 9. So just to show you the runtime, oops, I gotta click my overwrite because I have it. With giving it all of that, it's going to go really quickly, but on your laptop it might take a little bit longer. And as the neighborhood size gets bigger, it will take longer to calculate, so just keep that in mind. And so this is essentially a smoothing filter. You're taking the average elevation in that window and you're putting it into the center pixel. To calculate the prominence at that particular scale, we need to do a map calculation with the map calculator. And all we are going to do is to find the difference between the center pixel elevation and the average elevation that is in the middle. So just think about this in your mind a little bit. If we're talking about a peak where it should be higher, taller than the surrounding pixels. So if we take the peak at, let's say, 100, and the surrounding pixels are an average of 50 meters above elevation. 100 minus 50 equals 50. Okay? If we are a pit or a valley where we're lower than the surrounding average, then we do the same kind of math. Let's say it's 50 for the peak and 100 for the average. We would have 50 minus 100 equals minus 50. So the output of this is going to be positive when prominence is for peaks that stand up and dominate your view, and it's going to be negative for pits or valleys that go down and expand your view a little bit. They're like negatively present in the view of, as you experience the landscape at that scale of analysis. So what we will do, we will just take our regular DEM, and we're going to subtract the averaged LEV at each scale that we do this, at 9 by 9, 13 by 13, 17 by 17, etc. if you do more. And the name we're going to give that is topographic prominence at that scale, 9 by 9. Okay? We hit run on that, and it will create the map. Now I've already applied the color rules, but just to show you which colors you should apply, in the Define tab, by default it's going to be Viridis, which is the default color scheme. You want to pick Differences, and by default you might not see a lot of patterning, so you might want to click Histogram Equalization, and it should actually make it look like that. So histogram is just going to stretch those color values so that it really fills up the actual minimum, the actual maximum. And what we can do now is actually put that in the shaded relief so that you can see what that looks like. There we go. And we can zoom in like so and update our raster legend to match. Okay, so now we have these values of prominence at that 9 by 9 level. And again, deeper ravines or pits show up here in blue as negative numbers, and peaks or ridges, little knolls, etc. are going to be some shade of red. And that is the actual difference in elevation between the central pixel and the average in the 9 by 9 moving window around it. Now there are other algorithms that you can use to calculate prominence. There is in fact another add-on that I did not write, but it is available. It's called our Prominence, and it calculates a slightly more complex algorithm for calculating prominence. There's actually a good handful of algorithms. The one that I use here I think is the most intuitive. It's certainly the one that's most straightforward to apply in the GIS. But you can check out our Prominence and see how the different results look. You want to read the manual on this and kind of maybe go in to the paper, which actually is assigned in class, Marcos Llobera's paper, to see how he calculates prominence. It's similar but slightly different to the way that I've showed you here. Now the final thing that you're going to want to do is to calculate the global prominence. Where's my calculator? Oh, I have two of them. Here we go. And the way that we do this is after we calculate the prominence at all of the different scales that we did, so at least 9 by 9, 13 by 13, and maybe 15 by 15 or 17 by 17. What you are going to do is to do the average of them. Now again, there are other statistical measures that might make a little bit more sense, but a simple one to understand is how the pixels value changes over the different horizontal scales, and the average value is an okay way to do that, you know, at a basic level. So all we have to do is just put in our different ones. We're just going to add them, so we'll put a plus sign, 13 by 13, oops, 17 by 17. So at least these three, but you could go all of them. You want to put them within the parentheses, and then if you use 3 as input, you want to divide by 3.0. Haha, learn my lesson. If you had 4, 4.0, if you had 5, 5.0, etc. Okay? So this is the simplest way to do it, and of course you would calculate it, you would call it global prominence. I already did it at multiple levels, so I'm not going to overwrite mine, but you would hit run and it would create that. The other way to do it, and probably the more robust GIS way, is to do the R series and overlay. And with R series, you would then select all of the maps that you want to include, and I'll just go ahead and do it over all of them. Just, you know, select, 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 and then you can calculate several different measures that might actually be independently meaningful. The maximum, the minimum, the median, the average, and probably the standard deviation at least. And when you do this, it'll create a bunch of maps. It'll create one map for each of those. So you need to give them oops, this is the output map. Sorry. You put all the names of the input maps here, and then you put all the names of the output maps here. You know, average, max, whatever you want to call them, and you hit run, and it would calculate them. And again, it will take a little bit of time to do that. But what I'll show you briefly here at the end is the global prominence value that I calculated before. And I'll just go ahead and put that here. And, you know, we get, again, the spread from negative to positive, and what we're seeing here are parts of the landscape that are prominent compared to ones that are not. And again, if we want to put that again in on the shaded relief, it may look a little bit nicer. And you can get a real good sense. Let's put those towers back up. Probably shouldn't have them be in red for this particular one, so I'm going to give it color yellow. And there we go. We can see those towers on top of, let's make these guys big so we can actually see them. Right on top of the prominence. And really, if we were to zoom in on any of them, we'd see that they're not necessarily on the most prominent parts of the landscape. In fact, what we can do is to use our update attributes VWhatRast to upload the global prominence values into our table, and we can statistically analyze them inside the table, or at least just look at the values inside the table. I can't remember if I've already done that or not. I didn't, but let's just do that real quick. Where's my VWhatRast? Did I close it? Of course I did. Okay, let's just do that real quick, and that'll be the last of it. So, update attributes, VWhatRast, and vector points, Nabatean towers, existing map to be queried. We're going to pick our global prominence, like so, and attribute column is going to, I'm just going to call this GProm, just for ease, and we'll hit run. Vector map is not in the current map set. I just need to push that key there, and I think I should be able to do it. No. Okay. Do I have anything in here? Let me just make a copy of that. Make a copy, stick it in here, and that should in theory, fix my problem. So I just need to put it to the one that's in terrain analysis, and now I should be able to do it. Column not set. Oh. There we go. Okay, so let's remove that one. Actually, let me just change it to the one that I copied into terrain analysis. And now we can show the attribute data, take a look at the actual values that are in the table. And we have them over here, GPROM. So we have all of these values over here. And we can analyze those statistically by doing VUniver. Actually, VDB Univer, sorry. This is the one that we want. We can grab our GPROM like so, and we can get the average, minimum, maximum, and if we did the extended statistics, we could get even more information, including standard deviation, etc. And again, that could be meaningful or not. And we will analyze some of these values when we get into Project 3, when we start doing predictive modeling. But for now, that's basically it for visibility and prominence. And this will get you through what you need for Project 2.